Today we're going to talk about limits and continuity. Why am I excited? So we probably won't finish the topic, but I guess that's fine. You have a test tomorrow. Probably only get through limits, but that would be really good. And we're going to explain some of the differences between limits here and limits that you're used to. Now, limits is actually a super important topic. Like, how much we are going to deal with it is really going to be, you're not going to be able to appreciate just how important they are, but they are super important, because if someone were to ask you, for example, what is calculus about? Like if you were to explain in one sentence, what is calculus about? What would you say? Derivatives? That's it? Calculus about derivatives? Yeah, calculus is about integrals and derivatives, right? But what are integrals and derivatives?
Areas.
Limits, right? If you boil down calculus to this basic thing, the thing that you're studying all the time, the answer is going to be it's derivatives and integrals, but really those are limits. Calculus is the study of limits. Calculus in one word is limits, right? So limits is actually a pretty important topic, right? The derivative was a special limit, right? The limit of the difference quotient as the denominator goes to 0, right? And we know from Calc 1 and 2, well, maybe Calc 2. Where do you do limits here? Calc 2, right?
Calc
How do
1.
you did limits in Calc 1? Okay, cool. So, when you're doing limits, right, there were some things that had to fall into place for the limit to work, right? What were some of these things?
No zeros in the denominator.
Well, not necessarily.
Not necessarily.
Like when you have a function, the left side and the right side of the limit have to approach the same value in order for the function to be continuous.
Right, so let's say limits 2D, right? So we're going to keep things very informal, right? So informal definition, how would you describe a limit to someone whose math literacy is very low? Like, how would you do it? If I say the limit as x approaches a of a function is some number, what does that mean? Yeah?
F of x approaches that value as x.
Right. F of x will get close to this value as your x value gets close to a, right? So you know that a limit exists if there's some a value here and your function is doing this, right? And as your x values get close to a, right, from either direction, right, you're getting close to a from either the left or the right, your y value is approaching a certain number, right? Now the limit does not exist if this does not happen, right? So cases where the limit does not exist would be something like this, right? So, right, if you're coming from the left, you get a different value than if you're coming from the right, right? So these two things had to work, right? So limit was just sort of a way to tell where is the y value going if I know the x value is going somewhere, right? What is the y value getting close to as the x value is getting close to something? That's what limits was about, right? Talks about getting close to somewhere, right? Being infinitesimally small and arbitrarily close to something. That was the idea that you tried to capture with limits. And we tried to capture that also with a derivative where we're talking about the limits of the slopes of the secant lines, right? Now, it turns out there's something that's going to make things really different in 3 dimensions than in 2 dimensions, right? In 2 dimensions, all you have to do was look at 2 directions, left and right. Come from the left, come from the right. In 3 dimensions,
Top and bottom, left and right.
top and bottom, diagonally along this curve, right? If you're in 3 dimensions, how many directions do you have to check to verify that a limit exists? An infinite number amount, right? You have this point, and you want to know the limit as x, y, z. All right, so you have some function. Right? Just sort of explain the concept. I'll write down some formal definitions. Well, some not so formal definitions later. Right, so there's this point A. So there's the domain. Here's the point A, B in the domain, right? Now you want to say when you're as x, y, in a similar way, if you say the limit as x, y approaches a, b of f of x, y, right, which is just our function, which we call z, equals L, it's the same as saying your z value will approach a certain constant as your x and y value approach a certain coordinate, right? That's sort of the idea. But now the thing is that you have to check is, do you come from the left or the right? Or this side, or that side, or this side, or that side, or along this curve, or along a spiral, or along whatever, right? You somehow have to make sure that your limit will work no matter what direction you're coming from. You need to know this is what the z value is getting close to and x is getting close to something. Now in 2Ds it wasn't that bad because there are only two directions you have to check. In 3D though, there's an infinite number of ways you can approach a point. And so, you know, it's going to take like 42 pages at least to do a single one of these things. Well, actually, no. We're actually going to find very nice ways to check an infinite number of directions all at once. And it turns out that to prove that a limit does not exist, all you have to show is that two directions don't coincide. But that's basically the idea. And as you might have guessed, I don't know, this is actually going to greatly affect what a derivative means in 3 dimensions, right? See how vastly different the notion of a limit is? Well, that means that your derivative is not going to sort of be the same thing. Your derivative is sort of going to depend on what direction you're coming from. And these are what partial derivatives are about, but that's 11.3. But so far, that's where we're going. I just wanted to talk about the concept of a limit and how it's going to be different. Yes?
So when we're taking a limit in 2D, we're actually taking the tangent line on the curve, aren't we?
No? No, not necessarily.
Not necessarily. So we're not looking, again.
No. You're talking about when you're talking about the derivative.
The derivative is the tangent line.
The derivative, you're taking the slope of the secant lines to get close to the tangent.
In 3D, what are we doing?
Do you mean to find the derivative?
I mean, that concept. Are we taking the slope of something?
Sort of like the normal vectors of tangent planes of a surface.
So we're taking the slope of the normal vectors.
Right, so if you have like this random surface, a tangent line in 3 dimensions is really going to be a plane, right? There's going to be a plane that touches that surface at one point. Right. But it's, it's going to be sort of, we have to actually talk about partial derivatives before we go there.
Okay.
But, yeah. So derivatives, when you're talking about them in 3D, they're actually going to be quite different. Integrals won't be different so much, right? Because the integral is also a limit. Remember, it was the limit of Riemann sums, right? The thing is, those limits are usually nice. Nice in the sense that you never really divide by 0 in one of those things, right? Derivatives, though, the denominator is going to 0, and that causes things to act weird, right? So the derivative is going to be really different in 3D than in 2D. I mean, when we get down to the algebra of it, it won't be that bad, but conceptually, to make it all work, it's going to be, yeah, very different. But let's start with limits. Okay, so we talked about what the limit exists. So also there's a more mathematical way, like if a math major was proving a limit exists, there's this method that a math major would use called the epsilon delta method, which I'm not even going to talk about at all, because one, it's summer, most of you are math majors, and those of you who are math majors, if you take advanced calc 1, you're going to be doing tons of it anyway, so you're not going to lose anything. I don't really see the point of confusing everyone during the summer. So we're going to just do the easy method to find if a limit exists, which we use basically a higher dimensional order of the squeeze theorem, right? But that's what we're going to do. Use the squeeze theorem in 3 dimensions, and it's going to be an infinite number of directions, right? So now we're talking in layman's terms. If we say the limit as xy approaches AB of f of xy equals L, this means that your coordinate xy gets close to this coordinate AB from any direction, then your f of xy will get close to L. Or equivalently, the point ABL, the point AB f of x, f of AB will get close to ABL. Alright, so again, it's talking about things approaching. The only difference here is there are going to be infinite number of directions to check. It's really bad grammar. Not an English teacher, whatever. Way more than two directions, infinite number of directions. No matter what way you approach this point, you want to show that the limit exists. And so,
You have a little too many A's there.
how many A's do I have?
2.
Where?
Way.
It's way.
I think you meant.
No, I did that on purpose.
Oh.
The emphasis is way more than two. I did that on purpose. I'm not that bad at English. Jeez. Making fun. Okay. Okay. So again, at this point, if I was teaching in, say, a spring or the fall, I'd introduce the epsilon delta method. And so the concept of how we do is like around the point, we create a sphere, and we want to know that once we enter that sphere, the y value goes over. Right? I'm not going to talk about epsilon delta at all. We're just going to go to
descriptive.
the easy. It's just not worth it in the summer, I don't think. But let's I'm going to use 1A now since everyone's going to be messing with me. It's actually way more easy to prove that a limit does not exist, right? So proving that a limit exists means that as xy approaches AB from any direction, right, then your f of xy will approach L, right? It's actually pretty easy to prove that this doesn't happen when it doesn't, right? Than to prove that it does happen when it does. So let's actually do some examples so you can see that. Show that the limits exist. Xy approaches 0, 0 of this function. Okay. So the idea here is going to be saying that this limit equals to any number is going to be the wrong answer, right? Because it actually does not exist. Right? We're actually going to show later on how to show that something does exist. So the idea behind the limits is to show that it exists, it has to exist from no matter what direction you're approaching, right? Which means all we have to do is show two directions in which it doesn't work, right? So here's how it goes. We're actually going to pick the two directions that we want to show that they will give us actually different answers. Now, so let's let xy approach 0, 0 along the line x equals 0. Right? Let's say we're approaching the limit from that way, right? So in the xy plane, here's the origin, and I'm talking about approaching it on the line x equals 0, which is the y-axis, right? So I'm either doing this or I'm doing that. Right? Approach the origin from that direction, right? Then the limit is the same as the limit that 0y approaches 0, 0. Eventually we won't have to write this out. I'm just trying to be, I'm being very hand-wavy now. I at least want to write this down properly. Okay? So I'm pretending that I'm approaching from where x is 0. Now if x is 0, what does this limit give me?
0, 0, 0.
This gives me 0 over y squared. Well, that's just the limit of 0. Which is 0, taking the limit of a constant. There are no variables there anymore. Right? Now I want to show that there's another direction I can approach where I'll actually get a different answer. So I'm going to approach the origin, but now I'm going to approach from a different way. Which way do you think I can show?
Y equals 0.
Along y equals 0. Is that what you want?
Oh, I guess it
It would also give you 0.
would be
Right?
Y equals x.
Y equals x. Now, it's very important, right? So there are actually two things to mention there. Notice that choosing y equals 0 didn't add any new information, and it didn't help you to prove what you wanted to prove. It's also important to know that y equals x has to go through the point that you're considering. It turns out that y equals x actually does go through 0, 0. And that's why it's a viable choice, right? You could, for example, pick y equals x plus 1, because that doesn't go through the origin, right? So whatever path you're choosing, it has to actually go through the point you're considering, right? But now, in the case where you say y equals x, this means I can replace the x, y with x. So that would just give me what? X squared over 2x squared. And well, look at that. The x squares cancel. And suddenly, the limit is a half. Is it 0 or is it a half? Well, if it's giving me two different answers, it can be neither. It does not exist. Right? I approached from two different directions, I got two different answers. Right? This means that the limit does not exist. Because the answers had to coincide for it to exist. 2 points. I mentioned these, but let me write it down. right? In this situation, it gives the same answer, right? In general, you'd have to really look at your function to see how it behaves. But in this situation, choosing x equals 0 or y equals 0 gives me the same result. If I want to prove that I should get a different result, it would not be a path I want to pick. Second point is you must choose a path that goes through the point of consideration. In this case, 0, 0. Another thing that you should be aware of, if your denominator has several terms, it is best to choose a path that allows you to combine these terms. Right? So having 2 guys in the denominator, 3 guys in the denominator, bad, right? Because it doesn't. Why? Because you can't cancel across sums, right? You want to be able to put it in a situation where you can cancel stuff to get rid of the bad point. Now to do that, you'd want to sort of combine these two. In this case, making x equal to y allows you to combine them, right? Because you get both x squareds, right? There are other paths that go through 0, 0. For example, like y equals x squared actually goes through 0, 0. But making y equals x squared would make this x to the 4th, and then I can't combine the x squared and the x to the 4th. So it doesn't allow me to cancel very well, right? So I'm going to choose a path that allows me to combine these two, right? So you want to choose your paths wisely, right? So if you choose one path and you get an answer, make sure you don't pick another path that's going to give you the same answer. You're wasting your time, right? You're going to want to choose a path that goes through the point of consideration. You're going to also want to choose it so that it allows you to combine the denominators, right? So we just went through number 1 in a very long-winded way. So let's actually try to do B a little bit quicker now that we're a little bit wiser. Again, we're approaching the origin, but now my function is this guy. Remember, we want to show it does not exist, and you're told this, that they don't exist. Right? You're not always going to be told, but here you are. Okay? So, call this L. What's the first point you want to pick? You go along x equals 0. Then this would mean that your limit, if it exists, is just the limit as xy approaches 0, 0 of 0 over y to the 4th, which is 0. Okay, now what path do you choose? Y equals 0 would actually give you 0 over x squared, which is also 0. So y equals 0 is not a good path. Which one? X equals what? Okay, so let's see. X equals y squared. Does that go through the origin?
Yes.
Yeah, x equals y squared looks like this, right? It passes through the origin along that path, right? So that does go through the point of consideration. And in that case, my L would be the limit as xy approaches 0, 0 of. Now, if I replace all my x's with y squares, on top I would get y to the 4th. On the bottom, x is y squared squared. That also gives me y to the 4th. Well, that allows me to combine the denominators. And that gives me a half. This means L actually does not exist. So that's your answer. Again, another side note. Y equals 0 would give L equals 0, so not a good path. The path y equals x, right, which worked out so well last time. What would happen if I made y equals x this time? Then in this case, L would be equal to the limit as xy approaches 0, 0 of, if I let y equals x, I would get x cubed over x squared plus x to the 4th. Right? And now what would happen there? I could actually factor out an x squared maybe. That would give me 1 plus x squared. Right? This would cancel into that. I would have x over 1 plus x squared. Now remember my xy is going to 0, 0. That would give me what?
0 over 1.
It gives you 0 over 1, right? It would just be 0 again.
Which
right?
would give you the same answer.
So in this case, x equals y was also not a good path to choose. Right? So you'd have just gotten 0 again, which doesn't help you prove that it doesn't exist. Right? It's always best to sort of choose a path to combine things so that things could cancel out and you don't have something like this happen. That's why that last bullet point is important.
No question about notation, just the limit notation at the bottom of that of question B. Yeah. Is it okay to just leave it as x, y approaching 0, 0, or at that point should we put y squared, y?
You could do that, yeah.
It doesn't make a difference.
Technically, that's what you should put, but I won't penalize you. Right? Especially if you announce what path you're looking at here, then I just, yeah. Yeah, like I was saying, I'm not going to be too formal with this because limits, you can actually get so formal limits you'll want to rip your hair out. So just want to keep things relaxed. Just make sure you sort of understand the concept. Part C. This time we're not approaching the origin, we're approaching the point 1, 0. Show it does not exist. Okay, ideas?
I did it along x equals 1.
Okay, so along x equals 1, if I call this L, L would be the limit as 1 comma y approaches 1 comma 0 of y over 1 plus y minus 1. That just gives you 1. Okay, what was your other path?
Y equals 0.
Along y equals 0, fixing x equals 1, probably. Oh, no, y equals 0 does pass through x equals 1 eventually, right?
Yes, it works.
What
Yeah.
is this one? This one.
So y equals 0, because x equals 1 everywhere along this vertical line, but y equals 0 eventually passes through that. Y equals 0 is the x-axis. Okay, so along y equals 0, the limit is just going to be 0, right? So it's going to be the limit of x 0 approaches 1, 0. This would be 0 over x minus 1. This implies limit does not exist. Okay. Yeah.
If you choose one way and you get 0, and you choose another way and you get the limit as undefined, could that also lead to
Yes.
values?
Yeah. So undefined is not 1 in particular. So yeah. So again, undefined in a situation would also. Okay. That was fun. These ways by the squeeze theorem, but a higher dimensional one, sort of. Right, so theorem we will use says if we can find a function g of xy such that in absolute values f of xy minus L is less than or equal to g of xy, and at the same time the limit as xy approaches ab of g of xy equals 0, then in that case you actually have proven that the limit xy approaches ab of f of xy is in fact equal to L. Yeah.
What does that say after g of x1?
Equals 0. Can you see?
No. Above that.
Above that.
Such that. That was short for such that. Math people write such that all the time too, just like STH all the time. Why this works, you get a proof outline. I'm not going to be very pedantic about it. But here's basically what it shows, right? If you in fact found a function such that this is true, what does the absolute value of this inequality tell you can do? Positive and negative, how? What can you say?
Or sorry.
No, like in general, if you have like x is less than or equal to a, what does that imply? It means this, right? Remember, absolute value means that. Or you can actually put it between positive and negative. Okay, so that means if this is true, it means that this is also true. And now what you can do is you can take the limit of the whole thing, right? So the limit of minus g is going to be less than the limit of f minus L, less than the limit of g, right? But by assumption, the limit is 0, right? So I'm assuming that the limit as you go to a, b, limit as x, y approaches a, b, that's 0. So this would be 0. This would be 0, right? So we'd have 0 between the limit of f. Now, of course, the limit of L is just L itself.
Oh, so then you get the limit of f.
And so then I would have the limit of f is between L and L by adding L to both sides. But then the squeeze theorem says if you're squeezed between the same number, you have to literally be that number. The limit of f must be equal to L in this case, right? So if you can find a function where in absolute values this expression is less than that function and the limit goes to 0, it means that it forces your limit to be the L. Right? So that's sort of why it works. It's not very rigorous, but it'll give you a good idea. So let's actually show something exists using this method. Find the limit as xy approaches 0, 0. I believe I said x squared y over x y squared. Or sure it does not exist, right? So a lot of times they'll ask a question like this. Find this limit or sure it does not exist. So they're not really telling you which it is, right? So now, if I see a question like that, the first thing I'm going to try to do is prove that it does not exist, because that's easy, right? So I know how to pick paths that are really convenient. So, for example, approaching along x equals 0 gives me 0, and then I realize that making x equals y would allow me to combine the denominators, right? So let's actually do that, right? Along x equals 0, the limit is 0. Along x equals y, the limit actually gives me the limit x approaches 0, 0. On top, I would actually get x cubed over 2x squared. However, aside from choosing these guys to be 0, that was pretty much the best possible path I could pick, right? This gives me x over 2 in this case, though, which is also 0. Right? Of course, trying y equals 0, you get 0. Try x equals, if you try y equals x squared, you get 0. Right? You'd realize that you're trying a bunch of ways and you keep getting 0. Right? Even though you're sort of picking, which, based on your training, these are the best paths to pick. They both still give you 0. So it's sort of kind of hinting, maybe the limit actually is 0. Right? The problem is, how are you going to prove it? Right? You can't just show me, oh, these both work out, so it's 0. No, that's only 2 paths. There's an infinite amount you have to check. Right? Right? You could show me 1,000 different paths giving 0. It wouldn't matter. Right? I can always argue there's that one path you just didn't find yet. So how do we remove all doubt? This guy. Now the question is, how do I actually find a function g that gives me what I want? So we think L equals 0. So we must find g of x, y, such that if I take f of x, y, minus 0, it's less than g of x, y, and the limit as x, y approaches 0 of g of x, y gives me 0, right? That's what I have to find, right? I need to find such a function. So, here, f of x, y minus 0 is actually equal to what? Well, f of x, y is x squared y over x squared plus y squared minus 0. It's actually just equal to x squared y over x squared plus y squared. Right? How do I get a function that's bigger than that?
Add 1, maybe?
Add 1 where?
The numerator.
Hmm?
The numerator.
So you mean we want to do this?
No, you,
Do we know that goes to 0? As x and y go to 0?
just take out the y squared.
It's bigger, right?
Take out the y squared.
So you have x squared y over
S
y.
squared y over S squared.
Right. This is actually less than or equal to x squared y over x squared. Right? How do we know that?
Because you're adding something to the denominator, so that,
You're subtracting something.
no, I mean the original thing, x squared plus y squared. That's how you know it's smaller than,
Since we made the denominator smaller. Right? Fraction with a smaller denominator is bigger overall, right? If the numerator is the same but you have a smaller denominator, you get a bigger fraction. So one way to make a fraction bigger is to just make the denominator smaller. Right? And since y squared is either 0 or bigger, then removing y squared actually makes the denominator smaller. So I know that this fraction is actually bigger, but what's that fraction? Well, x's actually cancel. This is literally just a function y. Now what happens to y as xy goes to 0, 0?
zero, yeah.
Now this approaches 0 as xy approaches 0, 0. Therefore, choose g of xy equals to y, and the squeeze theorem shows the limit is actually 0. And all you have to do is just find a function that's bigger than it, that goes to 0 as you approach the limit, and you prove that the limit is actually whatever you assume the L is, right? If it wasn't 0 here, if I assume put a 5 here, right? Then the limit would be 5, right? It's whatever number you put here, right? The proposed limit goes inside the brackets here, right? L is your proposed limit. Did I do another example? Yes. Right, so again, this is coming back to algebra, you know, about how do you make a fraction bigger, right? You can either make the numerator bigger or the denominator smaller, right? And of course you want to do it in a convenient way such that things cancel out so that you get something that actually approaches 0, right? Let's try this guy. This is one we just did, but I'm actually going to show you another way to do it that's probably pretty cool.
Yeah, like I tried to, I chose another word problem to work on so I can get more practice with it on the computer, and it started doing the
Okay, does this guy exist? Well, if it does, we'd want to figure out what value it is. So let's approach along some convenient paths here. What path did you choose?
Y equal to 0.
Along y equals 0, L equals 0, right? Because sine of y is 0, this is 0, right? So you just have 0 over 2x squared, which gives you 0. Okay? What other path did you choose? You go y equals x, y allows me to combine the denominators. Right? L would be the limit of 2x squared sine x over 3x squares x squares would cancel. I just get 2/3 sine x as x goes to 0. That again gives me 0. Right? So those are two convenient paths. Can you be quiet here? So then we're thinking maybe the limit is 0. How do we prove it? Since 2x squared sine y over 2x squared plus y squared minus 0 okay, what do we do here?
We can use 2x squared sine y over 2x squared.
Okay.
We can remove
Because
it.
in the 2x squared.
So you can remove the y squared again. So we have 2x squared sine y over 2x squared. You wanted to see if you see that. These guys would actually cancel. That just gives you the sine y. And that actually approaches 0. So choosing g of xy equals sine y shows L equals 0. Okay. And of course, there are other cases where you might want to replace a sign with a 1, right? That would also work. In this case, it wouldn't work out that nicely. Or things like that, right? Because you know sine and cosine is bounded in absolute values by 1, right? So that might be beneficial sometimes. But in this case, again, removing the y squared was the way to go. We already did this, but there is actually another way to do this. Polar. Right? Why? Because we see that x squared plus y squared. One way to get it into a single variable, x squared plus y squared equals r squared. Right? So in polar, we know that x squared plus y squared equals r squared, and more importantly, as x, y approach 0, 0, r would approach what? 0. Right? X squared plus y squared. Both of these approach 0. R also approaches 0. So, the limit as xy approaches 0, 0 of x squared y over x squared plus y squared is the same as saying the limit as r approaches 0 of, now you replace these guys what they, you know they are. X is what in polar?
R cosine theta?
R cosine theta. So this is r squared cosine squared theta times r sine theta over r squared. Right? Now r squared gets cancelled. Now as your r is approaching 0, you just have this times 0 times that. That gives you 0. I've turned a 2-variable limit into a 1-variable limit by taking advantage of the polar coordinates parameterization. That's one more thing polar coordinates are useful for. Won't be the last time we see it. And I'll just end with something that almost goes without mentioning. You can just plug in the numbers if there's no problem, right? Here I couldn't just plug in the numbers because I'd actually divide by 0. But there are cases where you can just plug in the numbers. And in fact, what I've just written down is what we're going to talk about next. This is the definition of continuity, which is a mistake that a lot of people made on the quiz, but I guess I'll talk about that next time. Example. Limit as xy approaches 1 to 2. Of 2x plus 1 over xy minus 4. Okay. Now, if we were approaching 2, 2, this would be bad, right? Because I divide by 0, right? But approaching 1, 2 is actually not so bad because it's actually defined. The denominator is not 0 there. It means you can literally just plug in the numbers. So 2 times 1 plus 1 divided by 1 times 2 minus 4. This is minus derivative. And you can do this when the function is continuous, meaning it's defined at the point you're considering. And the very next topic is continuity, which is defined by this expression here. And we'll talk about that after the test tomorrow. So I guess that's it for today. So